When people think of the dawn of jet propulsion in the United States, the names that usually come up are General Electric and Westinghouse. The early pioneers that took concepts first proven in Britain and Germany and adapted them into American designs. Two of the most influential engines of that early period were the General Electric J36 and J50, each playing a role in shaping how the U.S. transitioned from prop-driven aircraft into the jet age. They weren't just pieces of machinery, they were stepping stones, bridging the gap between experimental wartime jets and the more advanced turbojets and afterburning designs that powered the supersonic fighters of the 1950s. To really understand these engines, it helps to break down their key features, performance aspects, design philosophies, and the unique selling points that made them stand out in their time. The J36 has an interesting backstory because it wasn't really an American invention from the ground up. It was derived from German technology captured at the end of World War II, specifically inspired by designs like the BMW 003. And it all electric! Already producing the J31, J, Sanju-san, and J35. Took this foreign influence and re-engineered it into a form that could be tested and manufactured domestically. The J36 was a turbojet with a single-spool design, an axial-flow compressor, layout, and thrust levels that were relatively modest compared to what came later. But the real selling point was in raw performance. It was the lessons learned from producing and testing it. It introduced American engineers to the challenges of axial compressors, which offered efficiency and compactness compared to the bulky centrifugal compressors of earlier engines, but also presented major stability issues like compressor stalls and surges. From a performance standpoint, the J36 produced thrust in the 3,000 to 4,000 pound range depending on the variant, which was enough to power experimental aircraft in test beds, but not enough for frontline fighters that demanded more acceleration and climb rate. Compared to the centrifugal J33, which had a reputation for being rugged and easy to maintain, the J36 was more delicate, requiring tighter tolerances and more precise operation. But it opened the door to a whole new generation of jets. When you look at the design elements, the J36 was slimmer and longer, optimized for aircraft that needed better aerodynamic integration. It represented the first real taste of what high-speed, efficient, axial-flow turbojets could do, even if the early versions were temperamental. Where the J36 becomes unique in the story is in how it connected America's wartime capture of German technology with post-war innovation. For the layperson, you could think of it as the prototype of the future rather than the engine of the present. It wasn't the star player, but without it, the team wouldn't have gotten to the championship. It taught GE how to handle airflow, how to manage materials that faced extreme temperatures, and how to push beyond the limitations of centrifugal compressors. And even though aircraft like the XP-59 and P-80 didn't rely on it, experimental testbeds gave engineers the data they needed to scale up thrust levels in subsequent projects. If the J36 was about lessons learned, the J50 was about application. By the time GE produced the J50 in the early 1950s, the United States Air Force needed a reliable, high-thrust turbojet to power second-generation fighters and reconnaissance aircraft. The Korean War was underway. Jet combat was proving decisive. And the US needed engines that could compete with Soviet MiG designs. The J50 was designed with thrust levels in the 7,000 to 9,000 pound range, with afterburning variants exceeding 11,000 pounds. That leap made it a true frontline engine, powering iconic aircraft like the McDonnell F-2H Banshee, the Douglas F-3D, and most famously, early variants of the Lockheed U to spy plane. Design-wise, the J50 was an axial-flow turbojet with multiple compressor stages and a robust turbine section. It benefited from all the hard lessons of the J36 and J35 programs, offering better fuel efficiency, higher pressure ratios, and more reliable operation at high altitudes. One of the selling points was its adaptability. The basic core could be scaled, modified with afterburners, and tailored to different aircraft. For the Navy, that meant reliable carrier-borne fighters that could take off in short distances and still pack enough thrust for dog. For the Air Force and CIA, that meant engines that could push a lightweight, glider-like spy plane to altitudes above 70,000 feet where no adversary could touch it. In terms of performance aspects, the J50 had some of the best altitude performance of its time. The U-2, for instance, depended on the J50's ability to maintain thrust in thin air at extreme altitudes. where other engines would flame out or lose efficiency. That single characteristic made it invaluable in Cold War reconnaissance, where endurance and altitude mattered more than raw speed. For carrier-based fighters, the afterburning version gave a surge of thrust necessary for combat maneuvering and interception. So, the J50 had a dual personality, efficient and reliable at high altitude for surveillance, but also powerful enough for short bursts of speed in naval fighters. If you compare the design elements of the J36 and J50, you see an evolution of philosophy. The J36 was slim, experimental, and very much about understanding the axial flow principle. The J50, by contrast, was bulkier, more robust, and designed for operational resilience. The compressor section in the J50 used more stages to squeeze out higher pressure rates, and the combustion chamber design was optimized to prevent blowouts, something earlier axial designs struggled with. The turbine materials were upgraded, using nickel-based alloys that could withstand higher temperatures, which was crucial for both performance and longevity. These weren't just incremental improvements. They were the difference between a lab experiment and a frontline weapon system. One unique selling point of the J50 was its role in bridging conventional fighters with specialized intelligence aircraft. Few engines can claim to have powered both carrier-based dogfighters and the world's most famous spy plane. That dual legacy speaks to the engine's adaptability and reliability. In layman's terms, it was like an all-purpose tool in an era when most engines were either too weak or too specialized. Pilots and engineers trusted the J50 because it could take punishment. It could be maintained under rough conditions, and it kept working where others failed. From a historical perspective, the J36 and J50 also represent two different eras in American aerospace culture. The J36 was born out of the scramble at the end of World War II, when the US was racing to catch up with Germany's head start in jet propulsion. It was about reverse engineering, experimenting, and absorbing knowledge. The J50, on the other hand, was born out of American confidence in the early Cold War, when the challenge was not catching up, but staying ahead, building engines that could outperform Soviet counterparts and enable missions that had never been possible before. Now, let's look at some of the performance numbers and compare them in context. The J36, at around 3,000 pounds of thrust, was underpowered for fighter use, but suitable for smaller aircraft or as a stepping stone. Its specific fuel consumption was high, meaning it burned fuel inefficiently, and its reliability was limited. The J50, in contrast, produced nearly 3 times as much thrust, had a far better thrust-to-weight ratio, and was more while it wasn't as advanced as later engines like the J57 or J79, it was the right balance of power and reliability for its time. Pilots who flew with it often remarked that it was forgiving, less prone to compressor stalls, and easier to manage during high-G maneuvers, especially compared to engines that were more temperamental. Technically minded viewers might be curious about compressor design, and this is where the J50 shines compared to the J30. The J36 used fewer axial stages, leading to lower pressure ratios and less efficiency. The J50 expanded this, using more compressor stages with better blade aerodynamics, allowing it to squeeze more air, burn more fuel, and generate more thrust without dramatically increasing engine size. For the audience less familiar with the jargon, you can imagine it like a bicycle pump. The more times you compress the air before lighting it, the bigger the explosion and the stronger the push you get. That's why the J50 could scale up in power without becoming a monster in terms of size or weight. Another unique selling point of the J50 was its compatibility with afterburners. Afterburning turbojets were still relatively new in the early 1950s, and not every engine was adaptable. The J50's combustion stability and turbine robustness allowed it to handle the additional stress of where raw fuel is dumped into the exhaust stream and ignited for a massive thrust boost. This capability was essential for naval fighters that needed quick acceleration off carrier decks and rapid climb rates in combat scenarios. For the J36, this was not even on the table. It was far too early a design, with no capacity for that kind of thermal and structural stress. Looking at design elements, both engines reveal the engineering culture of their eras. The J36 had a minimalist approach, taking what was available and making it work. The casings, the blade design, and the combustion chambers were all relatively simple, because simplicity meant survivability in the testing phase. The J50, however, was designed with maintainability in mind. It had modular sections that could be swapped or serviced, better sealing against oil leaks, and materials chosen not just for performance but also for durability under routine maintenance cycles. For the Navy, where salt, air, and rough handling were facts of life, that maintainability was a critical selling point. When discussing these engines, it's also worth noting how they shaped American aerospace strategy. The J36 contributed indirectly by feeding into the lineage of engines like the J47 and J57, which would become mainstays of bombers and fighters in the 1950s. The J50 directly influenced missions that changed the course of the Cold War. Without the J50, the U-2 wouldn't have been able to reach the altitudes necessary to photograph Soviet missile sites in Cuba, an intelligence breakthrough that directly influenced the resolution of the Cuban Missile Crisis. Few engines can claim such a strategic impact on world history, but the J50 can. For aviation enthusiasts, the appeal of these engines isn't just in their technical specs, but in their stories. The J36 tells the story of the chaotic rush into the jet age. Borrowing! Experimenting! Sometimes failing, but always pushing forward. The J50 tells the story of Cold War precision, of designing an engine not just to fly, but to serve strategic purposes at the highest level. Together, they illustrate how jet engines evolved in less than a decade from fragile prototypes to world-shaping technologies. If you put yourself in the shoes of an engineer in the late 1940s, the jump from the J36 to the J50 would have felt monumental. One was finicky, limited, and clearly transitional. The other was reliable, powerful, and a backbone of real-world missions. It's the difference between a prototype smartphone that barely functions and the polished devices we carry today. Both are milestones, but only one is practical for the mass. For a general audience, the key takeaway is that jet engines aren't just about thrust. They're about integration, reliability, adaptability, and mission suitability. The J36 might not have been the strongest engine, but it gave birth to knowledge that made engines like the J50 possible. The J50 wasn't the most powerful engine of its era, but it was one of the most versatile, proving itself in fighters, night interceptors, and high-altitude surveillance. That versatility is what gave it staying power in a time when aviation was changing faster than ever before.